Hi, this is Kaylee, and let's figure out this problem where we got a ball, which we're going to say is a hollow sphere, is rolling down this ramp into this vertical loop, and we want to know the minimum height we can drop that ball from so that it makes it all the way through this loop without losing contact. So the main focus will be at the very top. That's where it's most likely going to lose contact. And we're going to ignore any air resistance, but there is friction on this track so that the ball rolls without slipping. And that's an important key, that it rolls without slipping. That's going to help us actually solve the problem. So first of all, we've got a lot of information here. So we actually have two radii. One for the ball, which is this, and then one for the loop itself. So we need to designate those. So we're going to say R1 is the radius of the ball, and R2 is the radius of the loop. So we can keep them separated. And one important thing is that we actually need to figure out what's going on at the top up here. So if this ball was to just barely make it through the loop, then what happens is that centripetal force, that inward force, would normally be equal to, at the very top, gravity plus the normal force. But since this is barely making it, that normal force essentially goes to zero. So the centripetal force has to equal the force due to gravity at that point. And so if we do mv squared over r, which is mass times the centripetal acceleration, equals mg, the masses cancel out. And I want to solve this. So v squared equals gr, and so v equals square root of gr. All right, that could be handy later on. We're going to hold on to that. We're also dealing with a sphere, a hollow sphere. And the moment of inertia of a hollow sphere is 2/3 mr squared, and that's the radius of the ball, so that's r1. And this r, we don't want to lose track of it, that's actually the radius of the loop, so that's r2. So let me put that there. And one more thing, because it's not slipping, then we know angular speed could be substituted for velocity divided by the radius of the ball. So that's R1. Okay, I think we got things separated. So now, let's look to see what we got. We basically got an energy problem here. We're at the very top. When we release it, we just have potential energy. I use PE. If you want to use U, that's okay. That's at the top. Now, at this point, it is up in the air, so it does have some potential energy. And that potential energy at the top of the loop, let's put L for loop, plus it'll have some linear kinetic energy and some rotational kinetic energy because that ball is going to start to spin. All right, so let's map out what we got here. So we got mass times gravity times the height at the top, so let's call that h1, equals mg, and the height here, well, this height, that's equal to, let's see, there's a radius there and a radius, so that's equal to twice the radius. So the height there is equal to twice the radius. So I'm going to go ahead and substitute that in. 2r2 plus kinetic energy 1/2 mv squared plus angular kinetic energy is 1/2 I omega squared. All right, we got a long equation right there. Now what we're going to do is we could probably start finding these numbers here and dropping them in, but I'm going to go ahead and solve this algebraically to see if I can clean up this mess any at all. Let's first go ahead and take care of this term over here, this I omega squared, because we can substitute these in. So I'll rewrite mg height at the top of our ramp equals 2mg r2, which r2 is again r, radius of our loop, plus 1/2 mv squared plus 1/2. I'm going to go ahead and substitute. I is 2/3 mr1 squared. And omega squared will be v squared over r squared. So that'd be v squared over r1 squared. Now we got things in mostly similar terms. So let's see what we can do. Well, first of all, we can eliminate the mass from each term because there's one in each one. So we actually didn't need to know the mass to solve this. That's good. We've got r1 squared on the bottom, r1 squared at the top. So these cancel out each other. And that's what we got so far. Let's go ahead and clean that up some. So we get GH1 equals 2 GR2 plus 1/2 V squared plus this 2 and that 2 cancel each other out. So we end up with 1/3. The only thing else that survives is the V squared. Let's go ahead and combine these two terms here. So we get GH1 equals 2GR2 plus 1/2 plus 1/3. Well, if we do least common denominator, that's 6. So this would be 3 over 6. That would be 2 over 6. So that's really 5 over 6 V squared. Okay, excellent. Now let's see. We've got to have, our condition is that V has to be equal to square root of GR2. And so if we substitute that in, we get GH1 equals 2GR2 plus 5/6. Well, that's going to be squared, so that just eliminates the square root sign, so that's GR2. Oh, nice. We can actually eliminate the gravities out of this. So we can eliminate that and that and that. And so what we end up with, when it's all said and done, is the height we have to drop it from is equal to 2 5/6 the radius of our loop. Bam! Got it done. Now we can actually plug in our number. So let's see. We've got, let's see, 5/6 plus 2 equals that times, let's see, R2 is the radius of the loop, and the radius of the loop was 0.8 meters. So we're going to times that by 0.8. We get that we have to drop it from, we plug those numbers in. I'll do it over here. R1 equals 2 R2. H1 will equal 2 5/6 times 0.8. And we get 2.2, let's call it 7 meters. So it has to be dropped from nearly 3 times the radius of the loop in order to make it through. Let's see if we solve things algebraically. It may look like a mess, but we simplified it down to something really simple. Thank you, and tune in again, and I'll do this with something that doesn't rotate, and we'll compare the answers. Please like, share, and subscribe. Thank you. Goodbye.